Thank you very much. Yeah, thanks a lot for the opportunity to talk with you all. It is nice to be able to reach people a little farther away. I am near San Francisco in California. You guys can hear me okay, right? Someone give me a yes. Okay, good. Thank you. Yeah, so I'm near California, near San Francisco in California. That's where the SETI Institute is located. And so I'm a research astronomer there, part-time. I'm also a research astronomer at the University of California in Berkeley. And also the space science principal for Unistellar, so I lead some of the science programs for them. And what I hope to show you today is some of the science results we get from the citizen astronomers who have unistellar telescopes around the world that we work with as the professional astronomers to do real and meaningful science. And so I'll show you a bunch of different things. I'm going to share my screen. Hopefully this, let's see, hold on one second. Let's try this. And then, do you see a slide, a title slide? Yes, okay. Maybe. Zoom people, do you see a title slide?
Yep, we see it.
Okay, sorry, I can't see which way the thumbs are going, up or down in the big room. Okay. All right, so yeah, let me just get started. I'll try to keep this well under the hour that I have, so we have plenty of time for questions. If you have questions at any point, stop me however you can, either raise a hand in Zoom or just speak up. I don't mind being interrupted. That's cool. All right. Yes, so I'm presenting this unistellar network results. So that's what we call the group of citizen astronomers around the world who use these telescopes, presenting this all on their behalf. There's over 500 of those folks who have participated so far, and then also our science team, which is all these other people down here who do a lot of the work that I'll share. All right, go. Okay, so these are those people. We each kind of lead one of the different science campaigns. We have different science focuses that I'll talk about, but these are our folks. And then this is our office here in San Francisco, where we can do our work. All right, so let me just start by describing the telescope that I'm gonna be showing most of the results from.
Hey, Tom.
Oh, yeah.
The slides aren't changing on our view.
Oh, okay.
Yeah, you're in slide view.
Not full screen.
Okay, let me stop that. Oop. I wasn't sure if that would work, so that's fine.
There it goes.
Yeah, I will, hold on one second. I'm
Where's the share?
gonna stop sharing and come back to it. 1 second. Sorry about that. Go full screen. And we will try this again. After all this time, you would have thought I'd figure out how to do Zoom things. Okay. How's that? Is that better? Yeah.
There we go. Yep.
Okay. All right. Sorry about that. Yeah. So these are the folks that I was talking about. We have, I guess I might as well go through them. So Frank Marchis is the leader of the science team. He's also the chief scientific officer at Unistellar. There's me. I'll talk about what I do in a bit. Paul Dalba, he leads the Exoplanets program now, and used to lead the asteroid occultations program. Lauren Scrow, she kind of has a hand in all of the science programs and the science communication. Ryan Lambert leads the planetary defense program. Ariel Grakowski leads comets. And then Dan Peluso leads a lot of the education work that we do in various ways. All right, so yeah, the telescope that most of this data that I show comes from is made by Unistellar. That's the French startup company that created the EV scope, the Enhanced Vision Telescope. And it's a small 4.5-inch reflecting telescope. It has a camera built in with a CMOS sensor, and that's at the prime focus, unfiltered. It's on a motorized LTAS mount, and the real claim to fame, the power of the EV scope is that it is very smart. So it has a computer built in. It's all controlled through an app on your phone or your tablet. It does a lot of the hard work automatically, things like orientation on the sky, so you don't have to do any sort of alignment, it just does it for you. Go-tos are automatic, so you pick what target you want to look at from a very large catalog, and it will just go within 30 seconds or so. It's portable, it has a battery built in to last all night. And kind of for us on the science side, one of the key things is that as you record images with the camera, when you're done, you can then just upload those wirelessly to us. They go into the cloud where Unistellar and SETI can access them, and then we can actually turn the images into science. All right, and so what I like to say is the EV scope, you come for the enhanced vision, but you stay for the science. And so the EV scope, because it is smart and has the built-in camera computer, it allows you to see real-time stacked images on the for especially for deep sky objects from light polluted areas. And so basically, I won't go into too much detail of how it works because I'm really mostly going to talk about the science, but the telescope takes an image every 4 seconds, filters out the light pollution as well as it can, aligns it with all the previous images, and then averages those images together into a stacked image. And that's what you see in real time as you're looking with the telescope. So these are some examples of what you might get. For example, this comet image here was just 2 minutes of the telescope looking, and then on the right here, the pillars of creation in 30 minutes, and then a nice spiral. I forget which galaxy that is on the left in about 45 minutes. And so that's kind of the reason a lot of people get these telescopes, but we then try to convince them to participate in our science campaigns. And we've done that for a bunch of people so far, and you'll see some of what they've done. And really what we want to do is make it as easy as possible for people to participate in those science campaigns and do more than just kind of passively look at the sky, which is great. We want people to look at things on the sky. We know that's still engaging, but if we can get folks to learn a little bit as well about the science, then we think that's even better in terms of educating and getting people to be excited about astronomy, because there's more to it than just what you can see. And then one of the ways we make it easy is we put all the information you need to do a science observation on the Unistellar website. There's tutorials, there's video guides, there's all the predictions and things on when to look and where to look, and how to record it with your telescope. And there are specific modes built into the app to do all of this. Here are where our EV scopes are around the world. There's over 10,000 of the telescopes around the world right now. We've had, I think it's actually over 500 people who have participated in science campaigns already. So they've done at least one science observation. We have a Slack workspace that all of them can talk about. I heard you talking about a Discord space, Discord channel, it's similar type thing. And because I've worked on exoplanets and transients, I just want to point out, for those even those specific subtopics, we have hundreds of people who are in those Slack channels following along as we do things. We're trying to expand and get more people involved in the Southern Hemisphere. South America in particular, it should be growing soon. And everywhere else that we don't see a lot of yellow points, we're trying to expand however we can through some different outreach efforts. Okay, who are these people who are using these telescopes for science? And so it could be anyone, right? That's kind of the idea behind citizen astronomy. Some of them may be in the room. I actually don't know. I know Mike Prim is, I think, on the Zoom call. He's one of our more active members. If there's anyone else there who's participated and I missed you, I'm sorry, but I didn't see you. But yeah, they can be students. We do try to work with schools. I'll get to that in a little bit. People who have tons of experience with telescopes, people who have no experience with telescopes, people who live in the middle of cities, people who live out in the middle of the wilderness. We take all kinds, and all of them are able to do the science with the way we set it up. We have a bunch of partnerships on the professional side that we use to kind of facilitate the science campaigns. I won't go through all of these, but you may recognize some of them for asteroid work, for exoplanet work. NASA, we are now, so that the reason, sorry, let me go back a step. The reason that I, as a researcher at the SETI Institute, am connected with the Unistellar network is that there is a formal partnership between those two entities, where the SETI astronomers kind of design and curate and kind of bring to fruition the science campaigns, and we work with Unistellar to, again, make that as easy as possible and to get access to the data and to work with the network members. And this green line here, you'll see we're now an official partner of NASA due to a couple of grants that we got recently, specifically to do exoplanet work with citizen scientists, and I'll talk more about that in a second. Okay, so we have currently 4 major science campaigns that we are actively running. I won't talk much about asteroid occultations, but essentially we see asteroids in the solar system cross in front of distant stars when they temporarily block the light from that star, and we can learn about the shape of that asteroid. We can actually get it, and also a little bit about its orbit. Planetary defense, where we directly observe light from asteroids in the solar system. How from that we can again get a 3-dimensional model of the asteroid, actually, like we did here for asteroid 1999 AP10. And in particular, we focus on asteroids that are near the Earth, could potentially be hazardous someday if we don't keep an eye on them. And so we try to observe
Hey,
the
Tom?
ones that seem to be most interesting. Yeah.
Hey, sorry, you froze up for a minute there when you were talking about the planetary defense there. Would you mind repeating that real quick?
Sorry, yeah. So the Planetary Defense Program, we're mostly looking at these potentially hazardous near-Earth asteroids, ones that either that are on orbits that cross the Earth's orbit or might potentially come near the Earth someday. And we're just watching how the brightness of those asteroids varies over time. And from that, we get an idea of how it's rotating in space and how it's shaped and how large it is as well. All kind of good things to know if that asteroid might come real close to Earth someday, especially if they're kind of on a kilometer size scale and bigger. We can also print the 3D models we get out of that work too, and we send these back actually to the people who helped observe this. They got their little own 3D printed model. Exoplanet transits, I'll talk about that more in a little bit, but we are essentially observing planets in other solar systems as they're crossing in front of their star. Cometary activity sounds like, or is what it sounds like. We're observing comets, particularly as they brighten and get closer to the sun. And I'll also get to that, but we want to see how their appearance changes over time and what we can learn from that. And then there's actually now a 5th science campaign, transient event, that I am starting up, which is going to focus on essentially things that go boom in the night. They're events that come and go kind of without warning and fairly quickly. Things like supernovae, gamma ray bursts, microlensing events, quasars, so active galactic nuclei, things like that. And I'll talk a little bit more about that as well. So any questions real quick before I go on? I'll go into more detail about a lot of these, but I'll pause for a second.
Yeah, so with some of these projects, do you have like planned projects that the amateur astronomers in the network sign up to participate in, or do they just upload their data and then you process it and find things that match with the projects you're looking at?
Yeah, so we plan specific observations. So if I go back, so we pick out basically on a roughly monthly or even kind of yearly basis what the most interesting exoplanets and asteroids and comets will be to study, and then we advertise basically to say, please, if you're going to look, please look at this, take us some data so that we can do some science with it. But we also take, if you look at an exoplanet that we didn't pick, we will absolutely process that into results as well. We get that a lot. As another exoplanet that's interesting to you, you can go observe it and we'll analyze your data also. Okay, there's nothing else. I will keep going. Let's see what time it is. Okay. Okay, so yeah, let me start with a recent result. So you may have been following the NASA DART mission. This was the kind of wild idea that NASA could fly a spacecraft out towards a known asteroid and try to, well, intentionally crash into it in order to try and deflect it from its current orbit. This is just preparation for if we really need to do this someday to save our skin. And it was successful. So I think this is September 27th. The impactor actually did crash into the little binary asteroid moon of a larger asteroid, Didymos and Dimorphos. I think Didymos was actually forget now which one was the bigger one. But we were watching with our EV scopes as this happened. We had been observing the asteroid pair for weeks beforehand, and we've been observing it since. But we were actually watching while the impact happened, and Patrice Huet on Reunion Island off the coast of Africa caught this view. And you'll see, so this is kind of static frames turned into a movie, but you can see hopefully the faint line of the asteroid beforehand. And then when the impact happened, there was a cloud of dust that expanded around the asteroid and brightened. And then over time, that cloud kind of expanded more and then faded as it became more diffuse. Apologize, the label's in French because the company is French and so is Patrice. But this was, we thought pretty cool that we could see this in real time. You may have seen other videos from other telescopes as well who viewed this impact. So here's another view of the same thing from Kenya and Susan Murabana, who leads the Traveling Telescope program, which is a really cool program for public outreach of astronomy. If you don't know about it, I recommend you check it out. But here's another video of the asteroid coming in, and then you see the impact kind of ejects this cloud of dust off into space. Really, really cool. I thought that we could see this at all with our 4.5-inch telescopes. And we got this result the next day, I think. So very quick. Anyway, that was just kind of a fun thing. Just recently in the news. Okay, so let me get to some of the. I will get to more unistellar stuff in a second. I did want to just change paths entirely for 1 second to my other job. So this is some of what I do. And if anyone's interested in this at the end and wants to ask me questions, I'm happy to talk about it also. Most of what I did before I started working with the Unistellar citizen scientists was planetary system direct imaging. So using not small telescopes, but very large telescopes to point near infrared cameras, primarily, sometimes optical cameras, at young solar systems like this one in the top left corner that have these rings of material, rock and ice, orbiting them as planets are being formed. So this is kind of the building blocks of planets and then the leftovers of planets. And as you have all this material swirling around, it crashes into each other, and you basically grind up asteroids into tiny little grains of dust, things that are a micron across, smaller than the width of a human hair. And when you look at this, these systems with large telescopes in the near infrared, like these pictures here in the middle, you can actually see the starlight reflecting off of those dust grains. And there's so many of them, trillions and trillions of them, that you can see these rings. So sometimes like this one here in the middle, it's a nice, you're seeing it at the right angle that it looks like a nice circular ring. Sometimes they're tilted, just the way we're viewing them. Sometimes we see them only edge on, so they just look like lines on either side of the star. But basically we can study these and learn about how these planetary systems are arranged, how they're formed, and then connect them with our solar system and try to suss out, how they're the same, how they're different, where might we look more closely for planets in these young solar systems. And so we can follow up with things like the Hubble Space Telescope, which are the pictures on the right. And to give you an idea of scale, the pictures on the left here, this ring like this one here on the bottom right is kind of like the orbit of Neptune, maybe. What we're looking here on the right is much zoomed out, much more zoomed out. And so we're seeing out to more like the outer edge of our Kuiper belt, hundreds and hundreds of AU, even 1,000 AU away from the star. So these things are large and they extend a long way out from the star. And then just, I also look at exoplanets. And so this direct imaging is the only way we can directly capture light from exoplanets. All the other detection methods are indirect, looking at starlight or something else. And so we can do things like actually trace how to watch them orbit their stars, which is a video that Jason Wong made, part of this GPI's collaboration I was in. Is really, really cool, I think, to show that we can now actually watch exoplanetary systems moving over time. And of course, learn a lot more about their atmospheres and what those planets are like as well. Okay, that was a short digression. Let me get back to the exoplanet transit from Unistellar. I had mentioned earlier that we are now partnering with NASA through a couple of grants that we recently were approved for. And specifically what we're going to do here is observe exoplanet transits, which I'll explain in a second if you're not familiar with them, from candidate exoplanets that were recently discovered by NASA's TESS mission, which is a planet finding mission that's up right now. Space telescope that's the successor to the Kepler telescope. You probably heard of that. And our plan here is to specifically observe exoplanet candidates discovered by TESS that have very long periods. So they take hundreds of Earth days, or even a few Earth years to orbit their star. This means that you have to spend a lot of time basically following up those detections in order to confirm that those candidates are real, that they're actually planets and not some sort of false signal, and also learn more about what those planets are like, what their orbits are like. That takes many hours, days of telescope time, and we have lots of telescope time. So this is something that we're great at. It's also really helpful for us that we have telescopes all around the world. It means we can see lots of different parts of the sky, and we can also stitch together observations over time, which you'll see in a second. And so there's kind of 30, 40 of these targets that we can look at right now, and there's going to be more as TESS keeps finding them. And so you can see if you're interested on the right, kind of if you're familiar with V magnitudes, visual magnitudes for the host stars, they're kind of in the sweet spot for us between 8 and 14. And I'll get to the transit depth in a minute, but these are kind of a transit depth of 1 here is what Jupiter would show as if it were to orbit the sun. Okay. So what is an exoplanet transit?
Hey,
When I say
Tom?
that? Oh, yeah,
We have a question in the room real quick.
sure.
Tom, can you hear me?
Yes, barely.
Thanks. Sorry if you didn't review it. do you have any plans to let Unistellar control telescopes? Like, is there any plans to say, hey, I want to donate my scope to, Common Time and let you all do the heavy work on your controls and algorithm, or is it only astronomer driven, astronomer donated?
We've talked about this. For now, we really like the idea of having the citizen astronomers participating themselves. So of course, I would love to have as many telescopes to use as I can. But part of this is that we actually want people to be involved, taking the data, learning as they do it. And you still have to physically put the telescope outside as well. Things like that are hard to automate. But we can remotely control telescopes if we set it up properly and everyone agrees. But it's not part of the real plan yet.
Thank you.
Yeah, it's a good idea though. It's something that we've definitely considered. Okay. All right, yeah, so what is an exoplanet? So by exoplanet, I just mean it's a planet in a different solar system. Pretty straightforward. And by transit, I mean that the planet crosses in front of its star from our point of view. And so as it orbits, it just happens to be aligned. That orbit is aligned coincidentally with our line of sight. And so we can see that planet as it crosses the star. If we compared the planets in our solar system crossing the sun, this is what it would look like on the left. So Jupiter would block about 1% of the star's light. That's the 1% transit depth that I talked about. Earth is much, much smaller. It blocks only about 0.1% of the star's light. Actually, sorry, much less than that, less than 0.1% of the star's light. And so much harder to detect. So the way we do this is we just we measure the star's brightness over time. And as that planet crosses the star dims very briefly by that, say, 1%, and we can measure that. And this is what we call a light curve. So I'll be talking about light curves quite a bit. Okay, let's actually, yeah, I'll just quickly, repeat kind of what we can learn from this. So by measuring or confirming what the orbits of these planets are, we can help figure out how that solar system is arranged, and then of course compare it to our own. Not most actually, in fact, almost no other solar systems that we found are arranged like ours, where we have 4 small inner planets and then 4 large outer ones. They're all different kinds. We can also then use something called transit spectroscopy, where we measure the starlight passing through the planet's atmosphere to measure what the planet's atmosphere is actually composed of. Then we can look for signatures from water, for example, or oxygen or methane, these so-called biomarkers of what might indicate that there's life on those planets. We're probably not going to be looking in Jupiter-sized planets for those, which is what we're focusing on with the unistellar observations. But perhaps we can infer the presence of smaller planets, Earth-like planets, from what we know about the larger planets. That's something that we definitely try to do. Yeah, and that basically covers point 3 there. And so what are we doing with the unistellar network? Again, we have these telescopes all around the world. It means that we can spend a lot of time looking at these stars, looking for these transits by the exoplanets. And we're particularly good at the ones that take a long time to happen, more than, for example, a typical 8-hour night, or that we don't know exactly when they're going to happen. So we have to stare for a day or 2 or 3 continuously to try and catch it with that window of uncertainty. And then even the ones that we do know when they're going to transit very well, we can continue to observe those transits and look for changes, basically. Is that orbit of the planet changing? That's one way you can actually infer the presence of smaller Earth-like planets from the orbits of larger Jupiter-sized planets, is if that Jupiter-sized planet is slightly speeding up or slowing down in its orbit because of the gravitational pull from the smaller planet. All of our measurements have some uncertainty. So even if we think we know the period of that planet. We think we can predict when it will transit. Say if we want to point JWST at it to measure its atmosphere, there's some uncertainty in that. And so there's value to measuring those transits over and over and over again to kind of reduce that uncertainty and make sure that we don't waste James Webb's time when we go to point it at that planet. Okay, so this is kind of just a picture of what our images look like. So this is when we take exoplanet data, we have an image that looks something like this. This is a stacked image, so it's averaging together about 2 minutes of data from a single telescope. The target star is in the center in the blue circle. That one has the planet orbiting it. And then we choose just a comparison star nearby that doesn't have a planet, and we just measure the brightness over time. So the brightness in every image of both those stars and effectively divide them. And this is what we call differential photometry. And that lets us see how the brightness of the target star actually was changing without worrying about all the atmospheric effects. Whether someone turned the light on in the bathroom next to the telescope while you're observing, like a lot of that gets calibrated out when we do this approach. Okay, so let's see some actual results. So we did this observation last December. It was a transit that was predicted. It was a pretty well-known planet, HD 80606b, the so-called roasted planet, dubbed by NASA. It's because it's on an extremely eccentric orbit, so it kind of drifts pretty far away from its star. I forget exactly, something like Earth, an Earth-like separation, I think, but then comes in very, very close to the star due to that eccentric orbit, and really heats up by a few thousand degrees, I think, and makes it interesting just as a planet to study. And so there was a proposal that was accepted to observe this planet with James Webb and observe, basically make observations to study its atmospheric composition right when it was getting close to the star. So when it was as hot as it could be. And in order to know exactly what that time would be, they needed to know the period of the orbit. And for that, we were able to help. So we pointed our unistellar telescopes around the world at this expected transit in December. So you can see here in the little map that as the dark part reaches the telescopes, they flash on, start taking data in Japan, and then Europe, and then North America. Mike Prim is one of those telescopes there, the red label from Austin. And then when we took all of their data and measured that light curve, putting them all together on one common reference, kind of reference scale, we were able to build up this light curve here that clearly shows the planet crossing in front of its star. And we can measure the time to within minutes of when that happened. So this is what that looks like, kind of a static sense. So we observed for, in total, 27 hours with a few gaps, but not too terrible. And from there, we were able to measure that 1% dimming of the star to really high certainty, better kind of at the 5% of that 1% level. And we were able to measure kind of within the 15-minute or so range when exactly that planet crossed the middle of the star. And from there, this is combined with other data from some folks at NASA, and that informed now exactly when they're going to point James Webb at that planet in sometime in the coming months. Okay, so that's one case, roasted planet. Something else, for example, say the planet doesn't transit exactly when we expect it to. So these new candidates that are discovered by TESS, we don't always have the most information about them. We might get the wrong idea the first time. And so we've been observing these TESS planet candidates. They usually are named TOI number 0.01. So the 0.01 means it's the first candidate around that star. TOI stands for TESS object of interest. And we did this back in January of this year. Justice Randolph and Marty Mount observed from two very different places in the US and saw that this transit by this planet candidate started 1.5 hours later than NASA said it should. And so we said, well, that's weird, let's observe it again. So we observed it again in March. And indeed, it was still occurring 1.5 hours later than we thought. We had a lot more people participate that time. We got the entire transit. The first time we only observed the beginning. And then the second time we observed the whole thing. We were able to pass this information to NASA. Unbeknownst to us, someone had observed the same March transit and beat us by like a couple weeks with sharing the information. But essentially, we both came to the conclusion that yes, this original NASA orbit was wrong. They went back, looked at the test data, and revised the period of the planet. So they actually said, okay, it doesn't orbit every 3.14 days. It orbits every 3.13 days or something like that. So this is one of the key things we try to do is observe these new planet candidates that very few telescopes have observed before, and help really nail down what their orbits are so that we can go back and look at them later. And then let's see, there's 2 more of these results I'll go through. We believe, based on the published literature that we could find, that we just set the record for the longest period planet ever detected from Earth. So this is a 1,071 day orbit, about 3 years, by Kepler 167e. So again, this is a Jupiter-sized planet. This was actually kind of just a proof of concept that we could do this, because we needed the transit itself, the event, the planet crossing the star, took 16 hours. You cannot observe from one place on Earth for 16 hours unless you're like at the North or South Pole, and it happens to be the middle of winter or summer. And so we needed to combine many, many observations. We had 31 different citizen astronomers participate. We got all of their data. They all took some really impressive data from even bright places like downtown Tokyo, or like the middle of Tokyo, basically, to help build up this light curve. And it spanned about 40 hours. So we definitely caught in the middle that 16-hour span where the planet, the star was clearly dimmer, again, by about 1.3%, 1.4% in this case. And so this is about to be accepted by an astronomy journal. And this was actually written up by a French student as part of our SETI internship program. So this was kind of just, we didn't learn anything super exciting by this observation, but it proved that we could make it work, which is important for the next case. Now, I should just say also that, to brag for a minute, the previous longest period planet ever detected was something like 530 days. So we basically doubled the longest period that had ever been detected from the ground. Otherwise, you need a space telescope like Kepler or Spitzer Space Telescope, which actually is no longer operating, to do this. So we can save the time of those telescopes by using our little tiny ground-based telescopes instead. Okay, so then the last point on exoplanets then is what this NASA partnership is about. And so we have, in this case, for example, a planet candidate discovered by TESS, TOI 1812.01. It had only been observed to transit twice by TESS. And if you think about what that means, it means that we observed it, let's say we observed it to transit on January 1st, and then we observed it to transit again on March 1st, but not in between and not after. We don't know that transits didn't happen between January 1st and March 1st. So we know the longest that the period of that planet could be, that would be 2 months, but it could also be orbiting its star every 1 month. And then that means we missed a transit like on February 1st. Or maybe it orbits every 15 days or so on and so forth. And so we need to take the telescope time to stare at those potential kind of integer ratio periods to look for the next transit. And that's exactly what we did for this TOI. If for example, the period of this planet was something like 71 days, it would have transited on July 17th. It did not. We looked at it with a bunch of telescopes here. Light curve was flat, the star did not dim. no transit. Period is not 71 days. So we observed again on August 2nd. This is if the period were longer, something like 80 something days. Again, flat. The data points, if you average them together, are these blue squares. The red line is the expected dip if this planet were to transit. Those blue squares do not line up with the red line. It did not transit. So the period of this planet is not 86 days. So then we looked again on August 27th. This time we did the end of the dip. We didn't have data at the beginning. I think it was crossing the Pacific Ocean or something. But we caught the end. Thankfully, there's really nice data from Europe. And this means that, yes, indeed, this transit, this orbit was 112 days. And so now we know we don't have to go hunting now with our next observations in order to find a transit that we can study. We just know now what the period of this planet is. And again, we used citizen science data to do this. We didn't need big telescopes. Okay, and we're going to keep doing this. We've been successful. This was kind of the first success from this program, which just started in July. We've been successful with two more recently that are all being published and will actually be shared soon in a press release that I'm pretty excited about. I think this is pretty cool that we can do this. Okay. So just to recap, exoplanets, I don't want to fall too far behind here. We've done over 1,100 observations from citizen scientists around the world of exoplanets. That's 170 plus people. We're successful at roughly the 25% rate, excuse me. And we can do things like detect Saturn-sized planets over the course of many, many hours. And so this is something that no other telescope network in the world can do. It's not an exaggeration, that's actually true. And this is just people in their backyards, basically, doing this science. Let me pause again for a second while I take a drink of water for any questions on exoplanets, and then I'll go kind of more quickly through the rest. Okay, well, if there is nothing, then I'll just keep.
Hey,
Yeah.
Tom.
Mhm.
There was a question in the chat. It was more related to your direct imaging work that you kind of did your little sidebar on. They were asking like, what diameter and focal length telescopes we're using for that direct imaging. Diameter 10 meters. Actually, so for that we use things like the Keck telescope, which is 10 meters on Mauna Kea in Hawaii, or the Gemini South telescope was the one for the GPIS survey, or that main central picture, that's 8 meters. So giant telescopes, and then Hubble is 1 or 2.5 meters, whatever it is. So those are unique telescopes that there are not many of, but you need the large aperture, the large diameter in order to resolve very close to the star. So we're resolving angular separations there of tenths of arc seconds. So, many, much smaller than, the size of a full moon, for example, way smaller. We have another question in the room.
Hey, Tom, what kind of telemetry are these observations taking? Because I'm wondering how do you differentiate between, a multi-planetary system to ensure that you're seeing the same planet transiting?
Yeah, very good question. The answer is you can't always tell right away. And so ideally, like for TOI 1812, that one that I just showed where we think we nailed down that period to 112 days, we're going to keep wanting to observe that to make sure we didn't get really unlucky and catch a second planet that happened to transit at that moment. And so essentially just building up more observations is the way to determine if that's the case.
And would you be able to tell by the how much the star dims? I mean, unless the two planets were almost the same size, right? If you see two transits and they're different, the amount they dim the star is different. They're different planets, right?
Right. So that would tell you something for sure. You could get unlucky though if you have two very similar. We do know actually exoplanetary systems or planetary systems in general. You tend to see planets of similar sizes grouped together. The TRAPPIST-1 system is a good example. Really, really big in the news. Something like 8 super Earth-sized planets. They're all roughly the same size. They show the same transit signature.
Michael's right. He mentioned that the duration of the transit would be different. So you would just need to ensure that you're getting the same planet based on the transit time itself.
So transit duration, the actual length of how long the planet takes to cross the star, depends on multiple things. So it's not just the orbital separation and the period, but it also depends on the eccentricity of the planet and other things. So it could be similar enough that you might not immediately know from just a single transit that it's not the same planet, at least for our level of observations here. But yes, that's also a good point.
It was like further up.
Yeah, there was one pretty early, I think, yeah. Yeah.
A little bit more.
Yeah, I can't see the chat, so keep calling those out.
Yeah.
So this is how can you determine the difference between asteroid occupation, they may mean occultation, and atmospheric scintillation?
So for the asteroid occultation case specifically, that's like 100% blocking of the starlight. Like that star disappears for a second or a tenth of a second. So scintillation won't do that.
Is that just because you're looking at an asteroid in our solar system, and relative to the background star, it's so much bigger field of view?
Yeah, exactly. The angular size of that asteroid is larger than the angular size of the star, which is much, much farther away. There are cases where they're kind of on the same scale, and then the star only dims by like 50%, or it's a grazing occultation, and by 10%. Those are a little more ambiguous.
But it's much greater than a planet orbiting its own star.
Yeah, those are like I said, those transits are exoplanet transits are on the 1% level, whereas and they're much longer, whereas the occultations are on the 50 to 100% level, but only for a second or a tenth of a second. Okay, good questions. There's nothing else. I'll just wrap up with a couple more, two more quick science cases. And try to leave time for questions at the end. Okay, yeah, so comets. We can observe these as well. Of course, these are EV-scope images of comet C2017 K2 pan-stars. It's observable this year. I think at this moment, I think it's mostly observable from the southern hemisphere, but it's still visible. Early in the year, though, the northern hemisphere could observe it. And what we're trying to do with this program is build up these super images. So take lots of telescope images from different sites and combine them into one really high signal to noise deep image where we can see the detail in the nucleus of the comet, the coma, so the material around the nucleus of the comet, and the tail. And so you can see, for example, the main one here is the 23 observers who took data in Europe on July 21st of this year. But then on the right here, so that one's in the middle, and then we have also data from Japan on the top and North America on the bottom. They should show similar, they should show the same comet detail, just they have different amounts of data in them, so different final data quality. But from this, we can learn about what the comet is made of, and also how it's constructed, what its structure is like. And that can tell us actually more things about our solar system, which I'll come back to. and this color is real, by the way. This is the EV scope does RGB images, has 3 color channels, but we get those individual channels on the science side, and so we can balance them correctly based on what that comet color actually looks like. And so we can observe this, single comet, for example, on multiple nights. So July 14th, 21st, August 4th, August 11th, see how it changes. So the brightness will change over time. That's what these plots here show. The EV scope images, the EV scope measurements are a little hard to see here, but they're the colored point in the middle. And we can fit a model of how comet brightness is expected to change over time based on the properties of that comet to those data points. And in this case, that's the thick blue line. And it goes through the EV scope points, but it doesn't look like another model fit to much more data from other telescopes, which is the gray line and points. And the difference here, so the issue here, I should say, is that our data was only taken from a very narrow window in time, kind of in this July-August range. On the right, we see the same thing, but we have added data points earlier in 2021 from someone who observed this comet long before we were actually really interested in looking at it with their EV scope. And that really changes the constraints on the model, and we can actually match the model to the data much better. And that now agrees much better with the other observations as well. And what this allows us to do is that those models tell you about how that comet is shaped. So is it spherical? Is it rough and jagged? Is it kind of honeycombed, or is it a compact sphere, solid? What's it made out of? Is it really icy? Is it really rocky? Is it giving off lots of dust? Is it giving off no dust? Things like that. And that's really informative for us about the solar system, because these comets are kind of like time capsules. They were formed early at the beginning of the solar system 4.5 billion years ago, and they've just kind of been floating around ever since. And so a lot of them are kind of these primordial like record keepers of what the solar system was like early on. And so knowing a little bit about, if there was a lot of water ice or a lot of carbon dioxide ice or a lot of iron back then, is helpful to these evolutionary models for the solar system. You can see all the people here on the bottom right, for example, that contributed data to this one light curve for this comet K2. Okay, so that's all I'll say about comets. This is kind of just started up earlier this year, and so we're still getting a lot of it going, but we're already getting some good data from this. So let me, the last science campaign I'll talk about is transient events. This is the one I'm just starting up. Again, it's basically things that explode or go through some sort of violent change where they suddenly brighten or suddenly dim. We started taking data in June and processing it in July, and it's just getting to the point now where we can start sending out soon these kind of real-time alerts where we look for discoveries by all sky surveys, professional telescopes that are always scanning the sky for basically either a point of light that just appeared or a point of light that just disappeared. And then it sends out an alert online. We scan for those with automated servers. And then the goal is to, within 1 minute, pick out one that you can see, observe with your EV scope that's interesting to observe, and then tell you about it, either with an alert through the app that controls the telescope, or where it'll certainly be posted to a website. Maybe we can have an email list or something that people can join as well. And so that within a minute, maybe 2 minutes, you can be pointing your EV scope at this target and collecting data, which is really important, because a lot of these events, they change very rapidly on the time scale of minutes. So something like a supernova, like this movie is depicting, a lot of the interesting stuff happens in the first minutes or hours after that explosion begins. And so being able to quickly get data on it is really important to the science, and not something that professional grade observatories can always do, because there aren't very many of them. They're always being used. And sometimes you can't just interrupt what they're doing. And so having our telescopes be able to do that is really, really valuable. And so we'll not just only observe supernovae, but also things like gamma ray bursts, which are some of the most extremely energetic events in the universe. We don't really even know much about them yet, what causes them. We don't really know very well. So learning more, getting more data on those is really crucial. Active galactic nuclei, the giant supermassive black holes at the center of galaxies, they have these outbursts. Also really interesting of basically what they're eating. Micro lensing, you can actually find planets that way. That one is a little less clear what we'll do with it yet. And then novae, yeah, I'll get to novae in a second. Plus, who knows what else? We're hoping to find some things nobody even knows about yet. It's a little hard to see here, maybe on the right, but a supernova, an EV scope image looks like this. It's the little blue point of light at those red crosshairs outside at the very edge of this galaxy that hosts the star that exploded to produce this bright supernova. Okay, I said most of what I'm trying to do with this program, but basically we're going to measure the brightness of these objects over time. It's fun, they're unexpected, they come out of nowhere, can't predict them for the most part. And we want to become the quickest ones to do this follow-up observing so that we can specifically go after targets discovered by the LSST, the Legacy of Survey of Space and Time, which will start in 2024 at the Vera Rubin Observatory in Chile, which will kind of be revolutionary in finding these transient events that come and go on very short timescales. So we want to be part of that and actually be leading some of the science for that. And of course, we think LSST and other, even the surveys that are going on now are going to find new things that nobody knows anything about. We've never seen these events, these objects before. They're totally new. We think we can get data on those and help figure out what they are. And just to prove that we can do this, this is an observation of a nova. So this is a star that is not dying entirely, which is what a supernova would be, but it is accumulating material from its neighbor star. It's a binary. And after it accumulates enough, it basically causes fusion to occur on the outside of the star instead of in the core, and it blows off all the material that it accumulated in a nova. And so this is kind of a mini supernova, but it's still quite a bit brighter than the star normally is. And so these are observations from Scott Cardell in California, and you can see the nova fading over time, over the course of days. And so this change happens pretty dramatically. So you can see if I just look at the measurements. No, I took off the scale here, sorry. But basically, this is a 4 magnitude drop in V-band visual magnitudes from when we started observing it on June 10th to when we got our last observation on June 29th. So that's a factor of 40-ish. And we were really happy to see that our measurements lined up really well with professional measurements from the Zwicky Transient Facility, a telescope that's one of these all-sky surveys. And so our points overlap the gray points really nicely. You can see how the star was just flat. It was the same brightness, basically constantly for about 11 years. And then it spiked up, got dramatically brighter, and then slowly faded off over time. And so we can do this, we can do it quickly, and we're going to do a lot more of it soon. Okay, just about at the end here. I'm not going to go into this, but I just will note, if you are in education and you want to use some of our materials, we're developing activities and guides for students and teachers that use take advantage of the EV scope, but they're not strictly limited to, they're not only useful if you have an EV scope. You have an could be handy where we kind of walk you through looking at different types of galaxies or different nebulas that you can see and actually using real on-sky examples to do it. that's something that we have our grad student and education leader, Daniel Pluso, is working on. Lauren Scrow is doing that as well. And just the last note is if you're connected to a community college, we have a specific program called the Unistellar Community College Program or the Unistellar College Astronomy Network. You can either way, where we donate EV scopes to those astronomy professors at those schools so that we can train them to use the telescopes. They can then train their students to use the telescopes and use them for things like night labs or just star parties, or they're able to collect data and then do a small project on it where they can actually do hands-on observational astronomy that they might not have been able to do otherwise. And then also do science with the data they collect or even stock data that we give them as well. So we're in year 2 of this program, and I enjoy this. This is something we can reach a lot more people and a lot of different kinds of people than normally would have access to a telescope like this. Okay, so I'm just gonna stop there, and I'm happy to take any more questions that you have. Thank you so much for letting me take up your time. Thanks.
Tom, there was one question in the chat. Is there any room in the citizen science program for observations from non-EV telescopes or EV scope telescopes?
Yeah, so there is. So basically the observation planning, the observation designs that we come up with, they're good for anyone. Anyone who has a kind of imaging telescope setup can take advantage of those instructions that we post. What we won't do is we will not process those data on the SETI side. So for now, we have so much data, we do not have the time to process data from other telescopes, but we will combine our results with yours. If you can, measure your own light curve, send us the fluxes, we'll combine them like we did. One of those examples I showed you for the HD 80606b, the roasted planet, used data from other telescopes as well, and the Kepler 167e also, the very long one. So there is room for that. It's kind of more complementarity rather than us working with you directly, but for now, that's the best we can do.
There was another question. Have you detected any planets not orbiting stars or suns?
So I kind of, in general, yes. I mean, astronomers have found those. We have not within this unistellar network. But yes, these so-called free floating planets are actually could be very common. I don't know exactly how many have actually been confirmed, but I think it's probably on the dozens or hundreds level. The problem is they're kind of tough to find. You kind of just find them by accident as they occult a star, basically, or cause a microlensing event. But that's kind of unpredictable, and it's hard to find them after that. But
probably a better chance of seeing those on the large professional telescopes than the small aperture scopes.
Yeah, there are certain advantages to looking in the infrared, for example, as well. But there are estimates that actually there are many basically billions of these free floating planets in the Milky Way, for example. It's kind of wandering around because they get created in solar systems orbiting stars, but then between gravity and other dynamics, they get flung out when those solar systems are arranging themselves, and then they just until they interact with something else, they're out there floating around doing their thing.
Any other questions? All right, well, thank you again, Tom.
Thank you very much.
This is the one good thing about the pandemic is that we all learned about Zoom and we can do presentations like this. Okay,
Sorry, you muted. Yeah.
all right, anything else from anybody? What we're gonna do, we're gonna keep trying out new places to go and socialize and eat after the meetings. Today, we're gonna try the Posse East, which is right over here I don't know, the streets.
San Jacinto and Duval.
I'm sorry, yeah, San Jacinto and Duval, which is very close to the varsity where we're used to go. What you can do is, if you want to walk over there, it's fairly close. You can go to the other side of this building, there's an elevator, go down one floor, and there's a way that you can get out onto Dean Keaton, and then you go around the corner and back that way. So
Or go down the stairs directly across the hall and out the back.
that's
door.
true, yeah, there is that, I forgot about that, yeah, right. Jamie.
I wanted to mention about that. First off, Tom, thank you so much. Normally, we would take you with us.
Yes.
But you're a little too far away. Also.
I'll take a rain check.
Okay.
Hey, yeah, awesome. Come back to Austin. And also the kitchen at the Posse closes at 10, but then the facility itself, they stay open till midnight.
We were wanting to make sure that we finished in time so that we can get over there and get in on the kitchen hours.
There you
So,
go.
okay, if there's nothing else, we are
Thank you,
adjourned.
sir.
Yes,
Yeah, well, maybe everybody's familiar with Stephen Weinberg's book, To Know the World. It's, To Know the World is the title, and then the subhead is The Discovery of Modern Science. And he was a Nobel Prize winner.
he spoke to us twice.
Okay.
Yes,
All right.
yes,
So
we had him speak
everybody
twice.
knows.
Yeah, yes, thank you.
So
All right,
I'll look at that.
hope to see you at the Posse.
Great.